Hey guys, welcome back. Today we're going to be talking about gas particle speeds, how temperature and molar mass impact those speeds. I have an Excel spreadsheet that you can download to help you visualize how particle speed and temperature and molar mass all interact. And all in all, this is a very exciting topic, so let's go ahead and get started. Okay, to start off with, let's pretend we have an imaginary container, and my container has some gas particles in it, and you'll hear me throughout this tutorial or throughout this video refer to gas molecules or gas atoms as particles. They can be molecules or they can be atoms if it's a noble gas. I usually just refer to them as particles. So if our container has some gas particles in it, you know they're constantly moving, and something else specific about the way they move, if you'll notice, is that they are not all moving at the same speed. You got some that are moving fairly slow, some that are moving quickly. All right, let's go ahead and stop this. This gets kind of busy. Okay. In my imaginary container, there's only just a few, maybe 6 or 8 particles that are moving around. However, in a real system, there would be billions of these particles that are bouncing and moving, all at different speeds. Even if your container is actually at the same temperature, it doesn't matter. The molecules within that container are going to be moving at all different speeds. Now, this can be graphed, and this can be hard to grasp, I guess, at times, but this can be graphed in the way that we're looking at here by looking at the speed of the molecules and then the number of molecules that are at each of those speeds. So what that means is over here on this end of the graph, you have a very few particles that are actually moving very slowly. Of course, as you increase and you get to higher speeds, there'll be more particles that are moving at higher speeds. And then, of course, you taper off, and eventually you find that there's very few particles that are moving at these really high speeds. And so you get kind of this curve. This is called a Maxwell-Boltzmann distribution. And this curve kind of outlines how the particles are moving at different speeds. And I'm going to try to demonstrate that to you and show it to you as we move on. But the most important thing here to understand is that the particles are moving all at different speeds. And when we talk about these systems, a lot of times we talk about the average speed, or we might say the average velocity, and use those interchangeably, even though we know that velocity is a vector measure and speed is a scalar measure. All right, so let's take a look at how we can apply this and how we can, and what points or tips we can gain from this. Okay, and I'll start this back up, but one thing we need to understand is that this graph actually represents one particular system at a certain temperature. If I change the temperature, then of course we know that the molecules are going to speed up. They're going to move faster. If I cool it down, they're going to move slower. But this curve will stay basically a similar shape, but it may shift. It may shift to the right if this system gets warmer, or it may shift to the left if the system gets cooler. They'll still be moving all at different speeds, but the average velocity or the average speed will change as the temperature changes. Okay, so let's take a look at the formula that kind of defines the interaction between kinetic energy, mass, velocity, and temperature. So if we look at the terms here, don't let this complexity of this formula throw you. We're just going to look at some of the main points here, and we're going to pull some concepts from this. So if we look, we have M equals mass in kilograms, V equals velocity in meters per second, and we have K as a Boltzmann constant. It's a constant, so it doesn't change. And then T is temperature, and of course KE means kinetic energy. So if we look at this, there's a couple of things that we can glean from this formula that'll help us understand. First of all, kinetic energy and temperature are very closely related to each other. So if you look at the average kinetic energy of a system, it will be directly proportional to the temperature of the system. And you can see that, 3/2 obviously is a constant. Boltzmann's constant, of course, is a constant. So as the kinetic energy increases, the temperature increases, or vice versa. As the temperature increases, the kinetic energy will increase as well. They're interdependent on each other. Now, one thing we want to take a look at is if we lock down kinetic energy, of course, that also means the temperature is going to be locked down as well. If we lock those in place and leave those as constant, then what would happen if we change our mass, the mass of our particle, whether it be an atom or a molecule, or if we change the velocity? What would happen? If we look, as the mass goes up, the velocity will decrease. You say, well, why does that have to happen? Well, they have to multiply out to equal the same number because we're holding temperature constant, or kinetic energy would be constant by default. And so as we increase the mass, the velocity would go down. Or, of course, if we decrease the mass, the average velocity would go up. And one thing I want to point out too about this equation is that we have a bar over this. So we have an average kinetic energy, which is equivalent to 3/2 times the Boltzmann's constant times temperature, and that's also equivalent to 1/2 the mass times the velocity squared, but we have to take the average of this expression, so it's the average kinetic energy. Now, one thing I want to make sure that we do understand is you can't necessarily, if you know the average kinetic energy, or if you know the temperature, you can't back directly into the velocity. It doesn't work that way because these are averages. And I'll show you an example right quick that will help us understand how this works. Okay, let's look at a function that's similar to the one that we were looking at before, just so we can better understand why you can't back into the velocity. If you know the temperature, you can't back into that directly. Let's say we have x equals y squared, a similar expression to the velocity squared versus the temperature that we were looking at before. So let's take some simple numbers that we can square easily. Let's add those up, take an average. Now let's do the same thing for the other side. So we know that x equals y squared. So if we want to find the x in this, then we just square our values that are y. We can sum those up and take an average as well. Now, a little bit of algebra helps me to solve. I can say, well, I can take the square root of x and get y. However, if you try to take the square root of the average of your x values, because there was a square involved, it throws the whole thing off. It doesn't match the same average that you get if you were to average the values for y. So in the same scenario that you see here, it's also the way that it works for the equation that we looked at before. So if you try to solve for velocity when you know your temperature, then you're going to come up with something that doesn't really match the average velocity. It's going to be something that we refer to as the root mean squared, which is typically, in the cases that you're going to be looking at, is going to be higher than your average. It doesn't always have to be, but in the cases of the gas particle velocity, it's going to be higher than your average. All right, so let's take a look at another example and we can get a better idea of how this all kind of ties together. Okay, we're back to this graph that we saw earlier, minus the balls bouncing everywhere. And you'll notice we have those 3 points marked. You might have noticed them earlier. I didn't really say much about them. The first one at the top is what we would refer to as the most probable velocity. And what we mean by that is, if you look, that particular velocity would have the most number of molecules at a certain speed. So we would say that it's the most probable velocity for those particles to be at. Next to that, now the average velocity is going to be a little bit higher than the most probable velocity because you can see the curve kind of tails off to the right, and it actually drives the average velocity up higher than what the peak would be. If this curve were symmetrical, then the average velocity would be the same as the most probable velocity. And third, we'll have the root mean squared velocity. Now this velocity is, as I mentioned earlier, it's always going to be a little bit higher than your average in these scenarios. Mathematically, it doesn't have to be, but in the situation of molecular velocities, it's always going to be slightly higher than your average velocity. Okay, so we're going to hop over here to Excel, and we're going to take a look at how the mass of the gas, the mass of the molecule or atom in the gas, impacts the velocity or the average velocity. And what I've done, I've made a graph that basically compares the temperature with the average speed. And keep in mind, this is the average speed. So if I go to here where I've highlighted these, and I'll put this link down below so you guys can download this worksheet and you can use this to play around. I've not really locked anything out, so you could go in here and feasibly mess up these formulas, but don't worry about it. You can always just download another copy. So I've left everything unlocked so you can do whatever you want with it. Up here, I've highlighted the areas that you should change. Let's say we look at something like hydrogen, which is very light. It's going to be a molar mass of 2 grams per mole. And then we take a look at something that's heavy, like oxygen. We can see very clearly, as we would expect, as we increase the molar mass, it's going to be moving at a slower average speed. Certainly, I put our formula down here so we can reference that. Of course, as we increase this molar mass, our average velocity is going to be decreasing. And we can see that in the graph here. Now, of course, as we increase our temperature, our velocity is increasing for both of the gases, but it's the one that's a smaller molar mass is always going to be moving at a faster average speed than the higher molar mass. And just keep in mind that these are averages, so at each individual point, even though the average for one may be higher than the average for the other, they're made up of particles that are all moving at different speeds. I'm going to illustrate that, so hopefully we can better understand what we're talking about here. Okay, let's say, for example, just to give you an illustration that will help you understand the idea of graphing averages, we want to look at the change in average height as we move up through first grade, second grade, on up to 12th grade. Now, if we look at a first grade class, of course we know that class is made up of short people, tall people, medium people. They all go into this average. However, if we look at grade by grade, and we go from first grade to second grade up through 12th grade, obviously we're going to see the average height is going to increase as you increase your grade. However, we know that each individual grade is made up of students of various heights. So what that does mean is that you could theoretically have a first grader that's taller than a second grader, or even taller than a third grader if they're really tall. Or you could have a fifth grader that might be shorter than a third grader. However, when you take the average of each class as you move from first to 12th grade, the average height would increase. So this is very similar to what we see when we look at these averages that we're graphing for the gases. Of course, as we change the temperature, or we change the molar mass, we change the system, and the average will change. However, each one of those systems is still made up of particles that are all moving at different speeds. Okay, hopping back over to our Excel spreadsheet, you can see we've got the averages that are changing. We can put in something like nitrogen versus something heavy like carbon dioxide. That would be 44 grams per mole. And we can see the various differences in the way that those gases, the way the speed changes as we change the molar mass. Now, we want to look at one specific system and see, like we were talking about before, how each individual temperature and molar mass is going to have a range of speeds. Let's hop over here to our distribution tab. Let's take a look at that. So look at this chart over here that I've set up. Once again, I'll have this in the link below so you can download this and take a look at it, play around with it for yourself. The things that I've highlighted yellow are the things that you can change and play around with. So let's go back and let's look at this. So we had this carbon dioxide is 44 grams per mole. And if we want to see, we can see at various temperatures, it's going to have varying average speeds. Let's look maybe, for instance, at maybe 280. We see that the average speed is 367 meters per second. Let's hop over here to our distribution. Let's change our temperature to 280. We can see that when I look here, 367 is going to sit somewhere about here. So if you remember from our previous chart that we were looking at, you can see that these particles are distributed in that kind of bell-shaped curve. It's actually a Maxwell-Boltzmann distribution. It's not a bell curve. And you can see that in this particular case, I've only made my system have 1,000 particles. So if we look, what I've done is I've used a function to calculate the probability of each particle at each velocity. And then I've taken that and divided it by the total probability to get the fraction of particles, and then I multiply that by 1,000 in order to determine how many of those 1,000 particles would be at each speed. Now keep in mind, this is done in kind of buckets. In other words, of course I've got particles that are moving at 105 or 102 or 98 or 615. There's probably particles moving at all different speeds, but in order to kind of simplify this, this is a statistical method where you put everything kind of into buckets. So everything between 100 and say 150 would go in the 150 bucket. Everything between 50 and 100 would go in this 100 bucket. Of course, in a real system, you would have billions upon billions of particles, and you could make your buckets basically nearly infinitely small. and this curve would start to smooth out as those buckets get smaller and smaller and your particle count gets higher and higher. And so once again, as we look at this, in this particular case, at 280 degrees Kelvin, we're always in Kelvin with this, and a molar mass of 44 grams per mole, and we can see that we have about 8 particles that are moving in this 50 meters per second range. Then when we get up to this 3 to 350, we have around 126 particles that happen to fall into the 3 to 350 range. And of course, as you get higher and higher and higher, there's fewer and fewer particles. Now, looking and comparing this back to what we had over here, we had an average of, say, at 280, we had an average of 367. That's our average speed. Now, look at our distribution chart. That 367 sits about here. Now, if you remember, that average speed was a little bit higher than the most probable speed. Here, the most probable speed, well, it happened to fall right in this 3 to 350 range. But your average speed is typically going to be just a little bit higher. And of course, if we were to calculate the root mean squared, it would be 398.4. So it'd be a little higher than that. Now, what if we bump up the temperature? What happens? If we go up to, say, 320 Kelvin, you see that the curve starts shifting out to the right. And now our most probable speed is 350, or that bucket around 350. And now our average is 392. Our root mean square speed is 425.9. So we can keep playing around with this if we want to drop down to, say, something like oxygen, which is 32 grams per mole. We can see that the average speed increases. You see my average gets higher, 460. Now the graph starts looking lower and more spread out, but the actual average speed is increasing. Let's do something that will move quite a bit faster, maybe something like methane. When I look at methane, you can see the average speed increases, but it starts becoming more flat, more laid down as the particles are moving faster and they're spread out over a lot more speeds. See what happens when we raise the temperature up to 400. You can see we spread it out even more. If we drop that temperature down to 150 Kelvin, pull the graph back over here. Or if we increase our molar mass up to something pretty heavy, let's just make a number, we can see that we really drag our graph back over to the left and that our particles are moving. They're moving at an average speed of 199.2, and you can see that the reason this graph gets really tall is because there's not as many particles out here. They're moving, they're spread out over fewer feeds. So it's creating a tall peak graph here on this side. Okay, so you may be thinking, well, I mean, what about all these speeds out there? Are there no particles that are moving at this speed? Well, you know, when you get into a system that has billions of particles, and there's always a chance that you're going to have some that are way out here. If you look over here, the probability and the fraction number, so as I look at this, you can see that the fraction of particles is extremely small. 4.9 times 10 to the negative 44 means it's an extremely small chance that you're going to have a particle moving that fast. However, when you have a system that has, you know, like a mole of gas is going to have 6.02 times 10 to the 23rd particles in it. So there's always a chance that you can have particles that are moving at these higher speeds when you get these really big systems with a really large number of particles in them. However, with only 1,000 particles, it's very, very, very unlikely that you're going to see much past what you're seeing on this graph. All right, hopefully that was helpful, and maybe you understand a little bit better how these distributions work. Take a look at this. If you want, download this Excel spreadsheet. Just keep in mind, don't get too involved in the math. I didn't hide them. That way you can play around if you want to play around. Like I said before, if you break something, just download another copy. I wouldn't worry too much about it. That's why I left it where you can see how everything's set up. And hopefully this was helpful, and I will see you guys next time.